Welcome all. In this video, we will form 2:1 mux using transmission gate. Now before we start, we will see what is transmission gate is. So transmission gate, the symbol is shown in this diagram. Transmission gate is the parallel combination of PMOS and NMOS. This PMOS and NMOS, when connected in parallel, they will form a input terminal and this is the output terminal. Whereas gate of PMOS and gate of NMOS are called as control terminal. So this control terminal are connected to the complementary signal. So as shown in this diagram, PMOS is connected to S, whereas NMOS gate is connected to the S bar. And this is a simple transmission gate symbol. So when we are concentrating on this single transmission gate, when S is equal to 0, that time only D0 can pass to the output. Because when S is equal to 0, PMOS will be on, and at the same time as S is equal to 0, S bar is equal to 1. So my NMOS will be also on. So this particular switch, this particular transmission gate is closed, and so input can pass to the output. Now we want to form 2:1 mux. So we need 2 inputs and 1 select line. So this select line we have used in this diagram as a control signal, and D0 and D1 input as the input to the transmission gate. So here we need total 3 gates. 1 transmission gate, 2nd transmission gate and 1 inverter. We need inverter so that we can get S and S bar. So in layout, we have transmission gate 1, transmission gate 2 and the inverter. In the video number 1, we have seen how to do the design for the CMOS inverter. So that is why I have taken this inverter directly over here. We will just concentrate on the transmission gate. So in the transmission gate, we have selected a PMOS, then we have selected a NMOS. Please see over here, gates are not connected, but drain part and the source part of the NMOS and CMOS are connected, and well is connected. This is the N well, and that is connected to the VDD. So same transmission gate you can see over here. Then I need to, so I have selected this area and then I have make 1 copy of it. So now I have transmission gate number 1, gate number 2 and the inverter. Now let us do the remaining connection. You can observe over here, the gate of this NMOS is connected to the PMOS. So I will select a polysilicon. I will connect like this. Then the output of transmission gate is connected to the output of transmission gate 2. So I will take metal. Output of transmission gate 1 is connected to the output of transmission gate 2. That is nothing but this area. So that 2 connections we have done. As it is my output, I will give a visible node to it and will give the name as Y. Assign. Now as in the diagram we have seen, we need S and S bar. So to this inverter I will apply a clock signal, and that clock signal name we will give it as S. Assign. And output of inverter will be S bar. So this is S bar. But I don't want to see that into simulation. So not in simulation. Assign. Now output of this S bar, like output of this inverter S bar, is connected as the input to this particular gate. So I will extend that output like this, and I will extend the polysilicon as well. As polysilicon is highly resistive, I will use more metal part rather than the polysilicon. This I will increase the width of metal little more so that it can cover the polysilicon properly. Then I will select a contact, because when we are connecting two different materials, there will not be a connection. To have connection between that, we need different contacts. So in the palette, we can see the first option, and the name of that contact is contact metal poly. So select that and connect over here. So now, according to this diagram, we have completed this connection as well as we have done with this connection. Now the remaining part is we have to connect S over here and S over here. Now where is the S present? This is the S part, because we have connected this S, and then this S we supposed to connect over here, and the same S we supposed to connect it over here. So for that we have to take help of polysilicon material. So I will just adjust the design. Take polysilicon, extend it, and then remove the extra material with the help of gun. Right. Now again the polysilicon, extend this, please take care the width of the polysilicon should not exceed than 2 lambda, because it is very highly resistive material. Also the cost of this material is very high, so we should not use it in a excess percentage. Take polysilicon this, and it will be like this. Remove excess material. Okay, so if you compare with this diagram, we have connected S and S over here like this, S bar over here, and output we have connected. Now what is remaining? We have to connect the inputs. So for input we will be using this clock, and this will be my D0. Assign. Again select this and here will be my input, and this will be my D1. Assign. Now my connection is over. Now the thing that we have not done is we have not applied any power supply to the inverter, so that we have to do. So VDD to the PMOS, VDD to the PMOS, and ground to the NMOS. Now save the design and simulate. It is showing that the anvil is floating, so you will just cross check which anvil is not connected. Here this anvil is connected, this anvil is also connected. Just see where the anvil is not connected. Yeah, it's connected. So simulate. We will apply the VDD once again, and then we will do the simulation. Yeah. Now in the simulation we have D0 and D1, and then we have select line. Here if you see the change, the D0 and D1 are almost same, so we can't say that whether my input D0 is selected or D1 is selected. So what we will do, we will just rearrange the D0 and D1 first, and then we will see the simulation again. So I will make D0 faster. I will just double click on that and make it faster. I am clicking on the faster button thrice. Assign. So that change if you want to see. Over here we can see D0 is faster. So when select line is 0, D0 is selected. Now we will just adjust my D1 little more. This is my D1, and I will make it little more faster. Assign. So one more change we will see. We will make the D1 more faster, and then assign, and S we will make slower. Assign. Now we don't want to see many things over here, so I am just removing the delay and bus value and reset, so that clear waveform we can see over here. Now if you concentrate on this part, when select line is equal to 0, that time D0 is selected. See, in the output you can see the D0 pattern, and when S is equal to 1, that time D1 will be selected. So my S is working as a select line. When S is equal to 0, channel D0 will be selected, and when S is equal to 1, channel D1 will be selected, and that you have observed in the output. So in the output, this is the D0 channel and this is D1 channel. So this is perfectly working as a 2:1 mux. So when we have seen in this diagram, here we have used 2 transmission gate. Like if we compare with this, when we compare with this, we have 2 transmission gate, 1 inverter. Inverter we need so that we get S and S bar, select line and the inverted form of the select line. that we have applied as a control signal to the transmission gate. S is connected to the PMOS and the lower NMOS, whereas S bar is connected to this NMOS and this PMOS. And here we get the output of the 2:1 mux. So this is how we have simulated successfully 2:1 mux using transmission gate. I hope you have enjoyed the video. Thanks for watching.